Hello everybody, welcome to Unit 4, Analytical Trigonometry. In this video we're going to be talking about proving or verifying trig identities. Some people call it proving, some people call it verifying. They are two words that essentially mean the same thing when it comes down to what we're going to be doing. You could use them interchangeably. So first off, we are going to be using our trig identities again. So here is a quick look at all of those fun trig identities: reciprocal, quotient, Pythagorean, cofunction, and even odd identities. Hopefully you have a cheat sheet with all of these on it ready to go. So what are we doing when we talk about verifying or proving? So verifying means that I'm going to give you an equation with trig functions, and you have to determine that the left side does in fact equal the right side. So that's what verifying is, right? Verifying is essentially showing that the two sides are equal. So you're going to have an equation with something on the left side. We'll call that the left-hand side. And then you're going to have an equal sign. And then there's going to be something on the right-hand side. And you need to prove that the left-hand side does in fact equal the right-hand side. So a lot of kids think that this is actually easier than simplifying because, to be honest, it's like I'm giving you the answer. So imagine you start with the left-hand side and the answer is the right-hand side. So your job is to work the left-hand side, doing some good math until it equals or matches the right-hand side. Or you could start with the right-hand side and work the right-hand side until it matches the left-hand side. So everything that we did in the previous lesson oversimplifying is exactly the same that we're going to be doing here. The only difference is we kind of know the answer. Like, we know what we need to get to. We just have to get there. And that's what verifying is. Or you could call it proving, right? You're just proving that the left side equals the right side. All right, so let's briefly talk about some general hints to doing this. You could work with one side of the equation at a time. So you could work with the left side and make it look like the right side, or you could start with the right side, make it look like the left side. And something else you actually could do that is kind of rare, but it does work, is you could work both sides. You could work the left side for one or two steps and work the right side for one or two steps. And then whenever you get them to be equal to each other, that is proving or verifying that it is a true statement. So another hint is to always start with the more complicated side, right? The side that looks more complicated means there's more that you could do to simplify it. Starting with a simpler side, well, it's just less to do, so there's not a whole lot you could do. So we recommend you starting with the more complicated side first. As we did with simplifying, look for opportunities to factor, look for opportunities to add or subtract, definitely look for opportunities to use the fundamental identities, right? That's what simplifying was all about. Sometimes you have to create a denominator that has one or two terms, not two. And that's a little bit weird, but I'll kind of explain what that is as we look at some examples. And again, remember, there's that final technique that kind of always works. I want to say always, maybe 999 out of 1,000 times, is just converting everything to sines and cosines. If you could convert everything to sines and cosines, sometimes things start to simplify kind of on their own. But again, the most important thing is that you always try something. Don't just look at a problem and be like, I don't know what I'm doing. Sometimes you try something and it doesn't work. Sometimes you try something and it leads to a dead end, but at least you learn something through that process to not do again. So that's kind of something to think about. Now, it's super important that you understand what we're doing here, right? A lot of kids get confused by this. Let me do my best to explain this. Remember, we're going to have a left-hand side and we're going to equal a right-hand side. And it's important that you understand you cannot cross multiply. You cannot move terms from the left side to the right side. You cannot move terms from the right side to the left side. You have to leave the sides alone. And the reason for this is cross multiplying, adding to one side, subtracting to one side, those are all ideas that are built on you knowing that these two are equal. And I have to be honest with you, every problem I give you is a true statement, but the point is you have to prove it to me. If you start moving things side to side, that means you're assuming that you know they are already equal. But the whole point of these problems is that you're trying to show me that, using the identities, that the left side does in fact equal the right side. So at no point can you cross multiply. At no point you can say, oh, I'm going to move this +1 to the other side by subtracting 1. No, you can't do that. You have to leave the sides alone. So what can you do? Well, you could start with either side, but then you have to stick to that side until it matches the other side. Or, again, like I mentioned earlier, you could actually slowly work both sides, not maneuvering things side to side. Again, you cannot move things side to side, but you could work both sides down into a point that they match up, and that would also help you verify. Now, that strategy is not often used, but we will see some problems where it could be used. Now, again, I really want to be honest here. Verifying for most kids is actually better than simplifying. Again, I'm trying to be honest here. A problem that asks you to verify that identity is true is just really simplifying one side, but you know the answer is the other side. So you kind of know when you're done. Like a lot of kids complain that simplifying is hard because they just don't know when they're done or they get stuck. But listen, with verifying, you know the answer. The answer is the other side. All you have to do is get there and then voila, that proves you're done. So without further ado, let's dive into some problems. We're going to look at as many problems as we can in this video, and then you're going to try some problems on your own. All right, so here is an equation. We have a left side and we have a right side. Left side, tangent plus cotangent. Right side, secant times cosecant. Again, I'm allowed to start with either side, and the moment that I get the sides to match up is the moment that I am done. So I'm actually going to go ahead and start on the left-hand side. I'm going to turn everything to sines and cosines because I don't see any squares. I love seeing squares because then I think about the Pythagorean identities, but I don't see any. So I'm just going to turn everything to sines and cosines. So tangent is sine of x over cosine of x, plus cotangent is cosine of x over sine of x. And then now, well, the only thing I could possibly do is add these two fractions together. So I'm going to go ahead and add these two fractions together by getting a common denominator, cosine times sine. Now let's see here. This first fraction has the cosine. I need to multiply the denominator and the numerator by sine to generate that common denominator, and that's going to generate a sine squared on top, plus this fraction over here has the sine. I'm going to multiply denominator and numerator by cosine to generate that common denominator, and that gets me a cosine squared. And at this point, my eyes are jumping out of my eye sockets because I recognize sine squared plus cosine squared is one of our easiest Pythagorean theorems. That is equal to 1. So now I have 1 divided by cosine times sine, and I'm almost done because 1 divided by cosine, using the reciprocal identities, is secant. 1 divided by sine, using the reciprocal identities, is cosecant. And there you go. I have shown that the left-hand side is secant times cosecant, which is the right-hand side. So now that my left side officially is the same as my right side, I could stamp this with approved. So I wish I had it, but I wish I had a big stamp and I could just stamp it. Verified. I have verified this as a trig identity. The left side does in fact equal the right side. All right, let's try our hands at another one here. All right, so once again, I have a left side and I have a right side. What side do I want to start with? Well, the right side is pretty simple, sine squared, and we recommend starting with the more complicated side, so I'm going to start with the left side. Now, right away, I recognize a square and a 1. Oh my gosh, my eyes go right to those Pythagorean identities. What is secant squared minus 1? I mean, my eyes are just jumping out of my eye sockets. Again, you got to do a little bit of maneuvering here. And I'm not going to constantly show this because we've done this so much with simplifying. But if you go to this Pythagorean theorem right here, or Pythagorean identity, you can almost imagine if I subtract this 1 over to here, I get that secant squared minus 1 is tangent squared. Secant squared minus 1 is tangent squared. So I could replace the secant squared minus 1 with a tangent theta squared. Cool, pretty easy. All right, then at this point, I'm still like, all right, what do I do next? Well, again, sometimes when you hit a dead end, my strategy is to turn everything to sines and cosines. So I'm actually going to show you guys a different way of doing it. Again, there's multiple different ways you can do it, but check this out. Watch what I'm about to do. I'm going to break this apart, right? And this is going to be kind of weird, but bear with me here. A lot of kids like this. So I have tangent squared, but instead of dividing by secant squared, I'm going to multiply by the reciprocal, 1 over secant squared. Now, if you just look at this, it makes so much sense why these two statements are equal. I mean, you don't need a common denominator to multiply, so tangent times 1 over secant squared is tangent squared over secant squared. So all I did was kind of break it apart, but instead of dividing by secant squared, right, you could, and if you ever don't want to divide, you could always multiply by the reciprocal. So now look what I'm going to do. Watch this. This is going to be super cool. I'm going to take tangent squared and write that as sine squared over cosine squared. Again, that's just using the quotient identity. And then I know that 1 over secant is cosine. So that's a reciprocal identity. So 1 over secant squared is cosine squared. And then look at this. I got a big smile on my face. Those cosines are going to reduce to a 1. Cosine squared divided by cosine squared is 1. And I get a final answer, I'll squeeze it down here in the bottom, of sine squared, which is verified. I have officially shown that the left side is sine squared, and so is the right side. So I know that this is a true statement. Now, listen, I'm never going to give you a statement that it's like a trick, like, aha, the whole time it was false. Haha, I've tried to trick you. No, that's not my objective. Every statement I give you is true. You just have to show it to me. All right, let's try another one here. This is one of my kind of all-time favorites. I love this one. So I got a left side and I got a right side. Now, both sides don't look that simple to me, but the right side only has cosine. There's no other trig functions. So that's actually a hint to how I'm going to do this problem. So I'm going to start with the left-hand side, and what I'm going to do is I'm going to replace the sine squared, because I'm actually going to use the answer, the other side, as a hint to how I'm going to do this. And what I notice is that the other side does not have a sine squared. So I need to change the sine squared. What am I going to change that sine squared to? Well, go to look at the Pythagorean identities here. If I subtract the cosine squared to the other side, sine squared equals 1 minus cosine squared. If I were to bring that cosine squared to the other side, sine squared equals 1 minus cosine squared. So I'm going to go back to the problem here. And what I'm going to do is I'm going to replace the sine squared with 1 minus cosine squared. Now you got to be careful because I'm replacing a single term's sine squared with a binomial 1 minus cosine squared. So I got to be super careful that my next step would be distributing this minus sign. So I get cosine squared of theta minus 1 plus cosine squared of theta. Again, because the negative times the negative is a positive. And I'm just about done. Cosine squared and another positive cosine squared. Those are just like terms. 1 apple plus 1 apple is 2 apples. So 1 cosine squared is 2 cosine squared of theta minus the 1. There it is. Verified. The left side does in fact equal the right side. So what a cool problem that since I knew my answer, I was able to see in my answer, the right-hand side, that I didn't want the sine squared, so I replaced the sine squared with using the Pythagorean identity, and that easily led to my answer. Love that problem. All right, here is another one. This is a doozy, but I like this problem a lot. I think you will too as well. Clearly, the right-hand side looks a lot simpler. Right? There's not a whole lot I could do. I mean, yeah, I could use the reciprocal identity and say secant squared is 1 over cosine squared, but it's already simple enough. So I'm actually going to start with that left-hand side. And there's really not a whole lot I could do. Everything is already sines and cosines. It's all sines. And there's nothing squared, so I can't jump and use the Pythagorean identities. So the only thing I could do is do what it says, and that's to add. So I'm going to go ahead and get a common denominator. The best and fastest way to get a common denominator is just to multiply the two denominators you have together. So 1 minus sine times 1 plus sine. And I'm going to go ahead and multiply those together in the next step. But let me handle my numerators first. Here I have the 1 minus sign. I need to multiply by the 1 plus sign to get that common denominator. So of course I got to do that on top and bottom. So 1 plus sign times 1 is 1 plus sign. How easy was that? All right, this denominator over here has the 1 plus sign. It needs the 1 minus sign. So I'll gladly multiply as long as you multiply the top and the bottom by 1 minus sign. So I'm get positive 1 minus sine of theta. Now again, it was plus, so the plus sign is just right there. Okay, so let me clean this up and reduce. On top, 1 plus 1 is 2. The positive sign and the negative sign make a 0, so they're gone. So the only thing I have on top is a 2, which is good news because look at my answer. It has a 2. Now what about that denominator? Well, let's see here. Let's multiply it out. 1 times 1 is 1. Outside is a positive sine of theta. Inside's a negative sine theta. Yep, those are going to cancel. Give me a minute. And lastly, negative sine times positive sine is negative sine squared. So my numerator stays 2, but in the denominator, the positive sign and the negative sign are going to reduce to a 0, and I'm left with 1 minus sine squared. But wait a minute. I recognize a 1 and a sine squared. My eyes are going straight to that Pythagorean identity, and I'm not going to go to it because we've done it enough. You should recognize that if you subtract the sine squared to the other side, that I get 2 over cosine squared. 1 minus sine squared is cosine squared. And I'm almost done. So once again, you can essentially break this up. That's 2 times 1 over cosine squared. All I did was separate the numerator from the denominator, which you're allowed to do because multiplication does not require a common denominator. Or again, the other way you could look at it is all I did was I multiplied by the reciprocal of the denominator. You could always do that with division. Like even if you have 5 divided by 3, if for some reason you don't like that, you're more than welcome to do 5 times 1/3 multiplied by the reciprocal. It's the exact same thing. So again, the reciprocal of cosine squared is 1 over cosine squared. And hopefully you see my answer because I have 2. 1 over cosine squared using the reciprocal identities is secant squared. So voila, I just verified that the left-hand side is in fact equal to the right-hand side to secant squared. Another awesome problem that I just adore. All right, couple more here. All right, another problem, left-hand side, right-hand side. Clearly the right-hand side looks simpler. It's pretty basic, negative tangent squared. So I'm going to start with the left-hand side, and let me see here. Well, I actually see a bunch of squares in one, so I'm getting all jiggery here. Tangent squared plus 1 is literally one of my Pythagorean identities. Tangent squared plus 1 is secant squared of theta. I mean, that is really simple. And then what about cosine squared minus 1? Well, that's also a Pythagorean identity. I just got to do a little bit of maneuvering around. But actually, you got to be careful. This is where I'm actually going to take a moment to explain this. The Pythagorean identity is sine squared plus cosine squared equals 1. So now look at this. It says cosine squared minus 1. So I'm going to have to do a lot of maneuvering here, so please stay with me. I'm going to subtract the 1 to the left-hand side, and then I'm going to subtract the sine squared to the right-hand side. So on the left-hand side, the sine squareds are gone, and I have a cosine squared minus 1, which is what I wanted right here. But on the right-hand side, be very careful, it's negative sine squared, because I had to move the sine squared, and I had to move the 1. So that generated a negative sine squared. So I'm going to replace the cosine squared minus 1 with negative sine squared. So make sure you follow my maneuvering there. Hopefully you understand that. All right, now what I'm going to do here? Well, let's see here. Okay, secant squared, I could use the reciprocal identity is 1 over cosine squared. If you ever get stuck, turn everything to sines and cosines. It usually works. Times negative sine squared over theta. Well, once again, you do not need a common denominator to multiply. So if I multiply this out, I get negative sine squared over cosine squared. Uh-oh, guess what? Sine squared over cosine squared is tangent squared. That's a quotient identity. And then the negative still needs to be there. So don't forget the negative, which is, of course, in the answer. So I knew that negative needed to be there anyway. Verified. Left-hand side is, in fact, equal to the right-hand side. All I had to do was some use of the Pythagorean identities, and it worked out pretty simple there. Not overly complicated. All right, 2 more to go. All right, this is another one of my... I know I say it on every problem. One of my all-time favorites. Most kids yell at me. They're like, they're all your favorite. Well, they kind of are because I love math. All right, now to be honest, both sides look kind of complicated. Like neither side looks really simple. But I will say that if you look at the right side, it's all in sines and cosines. So there's actually very little I could do on that right-hand side. Whereas at least if I start with the left-hand side, I can change everything to sines and cosines. So let's do it. Secant is 1 over cosine of x. Plus tangent is sine of x over cosine of x. Now at this point, I'm just like super giddy because I already have a common denominator. I could add these bad boys together and I don't even have to work to get a common denominator. So I'm just going to add the numerators, 1 plus sine of x divided by cosine of x. That was my common denominator. Okay, but I'm looking at that and I'm thinking, boy, that kind of looks like the right-hand side, but it also doesn't. It's a little bit different, obviously. The cosine's in the denominator, and it's a 1 plus sign in the numerator, not the denominator. Oh boy. So this is an example of a problem where we're actually going to work both sides. So in terms of the left-hand side, I really just don't know what else to do. I got it about as far as I can. So now what I want to do is I need to start working with the right-hand side. And can I somehow get the right-hand side to look like the left side? And I'm going to use a strategy that is not an easy strategy, but it's a good strategy. I'm going to take the right-hand side, and I'm going to multiply it by 1 plus sine of x over 1 plus sine of x. Now, first and foremost, I'm essentially multiplying by 1 because anything divided by itself is 1. And if I multiply by 1, I'm really not changing anything. But why am I doing this? Well, because if I look at my left-hand side, right, I worked the left-hand side down as far as I could go. I'm looking at my left-hand side and I'm thinking, boy, I need a 1 plus sign on top. So if you need a 1 plus sign on top, why don't you just put one there? So that's why I said I'm just going to multiply the top by 1 plus sine of x because I know that my answer needs a 1 plus sine of x on top. But the consequence is that if you multiply the top by 1 plus sine of x, you got to multiply the bottom. But get ready, this is going to be a really good thing. All right, so in the numerator, I have cosine of x times 1 plus sine of x. But check out what's going to happen in the denominator, and this is the magic of math. When I multiply the denominators together, I got to do 1 times 1 is 1. Outside is a positive sine of x. Inside's a negative sine of x. Oh, that's going to be cool in a second. And then negative sine times positive sine is negative sine squared of x. So my numerator is still cosine of x times 1 plus sine of x. Nothing I could do with that yet. But my denominator is going to be really nice. Check this out. The sine of x and negative sine of x are going to cancel because they're going to add and make a 0. And then I'm left with 1 minus sine squared in my denominator. But wait a minute, red flashing lights, you should recognize that as a Pythagorean identity. If I take 1 and subtract the sine squared, 1 minus sine squared is cosine squared. We have used that enough. Again, we've used it so often that I shouldn't have to keep writing it, but I will show you it real quick. There's the Pythagorean identity. If I subtract the sine squared over, I get 1 minus sine squared is cosine squared. And now I'm almost done because this cosine on top will reduce with one of the cosines on the bottom. Right? Keep in mind that cosine squared is cosine times cosine. So one of the cosines on top will cancel with one of the cosines on the bottom. So what's left is a 1 plus sine of x on top and a single cosine on the bottom, which is amazing because now my left side is equal to my right side. Verified. I could walk away knowing this is right. So listen, not gonna lie, definitely a tougher problem, definitely some unique strategies that I did in this problem, but this is a good example of a problem where sometimes you gotta work both sides to get them to match up. And as long as they match up at some point, you are correct. On one more problem, and it's definitely a good one, but you're actually gonna realize as hard as this one looks, it's really easy. All right, so this time the left-hand side looks pretty simple. I mean, I don't know if you can get much simple to tangent to the fourth. Now, I don't love fourth powers, but at least there's only one trig function, tangent to the fourth. So what the heck can I do on that right-hand side? Well, I noticed that I have two terms. Terms are anything separated by a minus or plus sign. So I have tangent squared, secant squared, that's a term, and then the other term is tangent squared. So what I'm going to do is I'm going to factor out, again, this is using a factoring technique, I'm going to factor out a tangent squared because both terms have a tangent squared. So what's left is secant squared of x minus 1. Again, I have to leave a 1 there because when you factor out the tangent squared on this first term, if I take away the tangent squared, I'm left with secant squared. And on this last term, if I take away the tangent squared, I got to leave something there. I can't leave a 0. I'm just going to leave a 1. And again, please distribute to verify this in your brain. Tangent squared times secant squared is tangent squared secant squared. And tangent squared times negative 1 is negative tangent squared. But what's beautiful is check this out. I instantly recognize, again, anytime you see a square with a 1, you should instantly recognize Pythagorean identities. Secant squared minus 1 is tangent squared. If you really need help with this, just remember the identity. Tangent squared plus 1 equals secant squared. And if I subtract that 1 over, I get that secant squared minus 1 is tangent squared. So I could replace the secant squared minus 1 with tangent squared. And now it's pretty obvious. Tangent squared times tangent squared is tangent to the fourth. Say it with me on 3. 1, 2, 3. Verified. I have shown that the left side does in fact equal the right side. So verifying or proving, it means the same thing, is essentially you have two sides. You need to make one side look like the other. Or you could work both sides slowly. But you cannot work both sides across each other. You can't cross multiply. You can't add one thing from one side to the other. Or you can't subtract. You got to work individually with one side at a time. Work the left side until it looks like the right. Work the right side till it looks like the left. Or work both sides individually until they match up. And the cool thing about this is, like I said, you know you're done when you got it done, right? You essentially already know the answer. In fact, in the past, I'll get kids that try to pull a quick on it. I'm not this dumb, but I mean, I'm not an IQ of 150 or anything, but I'm not stupid. I'll get kids that they'll have a left side and a right side, and they'll just write a bunch of gibbly glunk, and then they put their final answer as they, like, let's say the right-hand side was secant. So they'll do a bunch of work, all wrong, but they'll put secant as their final answer. And they think that I won't look at their work. And they'll say, hey, left side equals right side, I'm verified. And I'll say, yeah, but none of your work shows how you got secant. But hey, I'll give the kids an A for effort there, right? I mean, at least they tried to fool me by just doing a bunch of nonsense and thinking that I wasn't going to look at it. So again, you got to show your work that, because again, you know the answer is the other side. You just got to make sure you show the work in terms of how you got there. So good luck on this. You're going to get a worksheet over verifying or proving. Most kids struggle with this a little bit, but then eventually they get the hang of it and they use their identities and they're not too bad. So good luck, and I'll see you guys later.